Let us take a look at question number 2. A curve has the equation of x squared over 1 plus x squared plus y squared over 1 plus y squared is given as being equal to x cubed times y to the power of 5. And you are told find the equation of the tangent to the curve at the point 1, 1. Okay, so we need to find the equation of the tangent to the curve at this point. And then we are supposed to give the answer in this general form of ax plus by equal to c, and where a, b and c are supposed to be integers. And of course if we solve this, we're going to get 6 points. Okay, so of course when the question says find the equation of the tangent, so we know that we need to find the first derivative in order to be able to determine what's the gradient of the tangent. So we're going to start differentiating this function. So we are going to differentiate with respect to x. So let's start with this x squared over 1 plus x squared. So since this is x squared over 1 plus x squared, we can see that we have to apply quotient rule on this. So we're going to write the denominator, which is 1 plus x squared squared, okay, because you recall it should be a v squared. And then we will have to, of course, when you're using quotient rule, you have to be careful. You got to start with the denominator function first, which is 1 plus x squared, and then the derivative of the numerator function. So if we differentiate x squared, it's going to give us 2x. We bring the 2 to the front and x, then subtract away a 1 from the power, so we get 2x. So we have done half of the problem. So now let's go to keeping the numerator fixed, which in this case is x squared. So we're going to keep the x squared fixed, and we're going to differentiate the denominator, which is 1 plus x squared. Of course, when you differentiate a 1, you get 0, and x squared, if you differentiate, it still becomes a 2x. So we have fully differentiated x squared over 1 plus x squared. Now let's go to the differential of y squared over 1 plus y squared. So as also we're going to apply quotient rule on this. So let's keep the denominator fixed, which is 1 plus y squared, and we put a square. And then we're going to start with the denominator function, which is 1 plus y squared, and we're going to differentiate y squared with respect to x. Please remember that. So when you differentiate with respect to x, you have got to differentiate it implicitly. So we're going to bring the 2 to the front, so 2y to the power of 1, and you got to differentiate y once more, and that would give us dy dx. So you got to write 2 times y, okay, because we are differentiating with respect to x, so we need to differentiate the y with respect to x, so that should give us a 2y dy dx. So we are done with differentiating the numerator. Now let's keep our numerator fixed, which is basically y squared, and we're going to differentiate the denominator. Of course 1, if you differentiate, it's going to become a 0. However, y squared, when you differentiate implicitly, it would become 2y dy dx. So now we are done with the left hand side of the expression. We have differentiated them with respect to x. Now let's go to the right hand side, and once again on the right hand side we can see that it is a product of two functions. Therefore we are going to use product rule. So we're going to keep the x cubed fixed, and we're going to differentiate the y to the power of 5. So what would it be? So you bring the 5 to the front, and the power would become a 4. So 5y to the power of 4, and since we are differentiating with respect to x implicitly, we need to differentiate the y with respect to x, so we're going to write the dy dx. So now let's keep the y to the power of 5 fixed, and we are going to differentiate x cubed with respect to x. So that would simply become 3x to the power of 2, so 3x squared. There we have completely differentiated this entire expression given as such. So now all that we need to do is to find the value of dy dx when x is a 1 and y is a 1, and that should give us the gradient of the tangent. So now we could simplify this, okay, so that the substitution and simplification would become easier. So 2x times 1 is of course a 2x. 2x times x squared is going to give you 2x cubed, and then here I have got another minus 2x cubed. So as you can see later in the next step, 2x cubed minus 2x cubed can cancel, so the numerator is just simply going to become 2x. So that will be an easy expression than looking at this. So if we go to this expression, so 2y dy dx times 1 is of course 2y dy dx, and then we have got a 2y times y squared times dy dx, which is going to become 2y cubed dy dx. Then let's expand this second bracket after the subtraction. So minus 2y cube dy dx. So once again we can see that these two expressions can get cancelled with each other because they are exactly the same. The denominator I didn't touch, so I'm just going to leave it as 1 plus y squared squared. Then now let's go to the right hand side of the expression. So let's rewrite it decently. We'll write the number in front, 5, and then followed by x cube, and then followed by y4, y to the power of 4, and then dy dx, plus this part will become 3x squared times y to the power of 5. So that's the simpler expansion or simplification. So now let's cancel the 2x cube with the 2x cube, and similarly in this fraction let's cancel the 2y cube with the 2y cube dy dx as well. So if you look at the first fraction, it is simply 2x over 1 plus x squared squared, so which is what I have copied down. And then in the second fraction, 2y cube dy dx can be cancelled with a minus 2y cube dy dx, so that leaves only 2y dy dx as the numerator, and then divided by 1 plus y squared squared, so which is copied down. And this right hand side I didn't touch at all, so it's just copied down as it is. So that's the simplest form that you could bring it into. Now let us substitute the value of 1 1, because the tangent passes through or the curve actually passes through the point 1 1, and that's where we are interested to find the equation of the tangent. So we could just replace the x with x coordinates with 1 and the y coordinates with 1 as well. So if I substitute 2 times 1 over 1 plus 1 squared, that's what I have here, and then 2 times 1 dy dx, which would be simply 2 times 1 dy dx divided by 1 plus y squared also, which is of course the value of y is a 1, so it's a 1 squared squared. And then on the right hand side, similarly 5 I have copied down, x cube is 1 cube, and y to the power of 4 is 1 to the power of 4. And then for this part of the term, so x and y have been replaced with the 1 respectively. So now if you look at this expression, the only unknown is dy dx. So you find the dy dx, that means you already gotten the gradient of the tangent. So that's a 2 over 1 plus 1 squared is of course 1 plus 1 is a 1 squared is of course a 1, 1 plus 1 is going to be a 2, 2 squared will become 4. So but let's just write it as 2 squared first. So this part is simply 2 times 1, which is 2 times dy dx, and this is also 1 plus 1, which is 2, then you got a 2 square, is equals to 5 times 1 cube and 1 to the power of 4, all will become 1. So it is simply going to be 5 dy dx plus 3 times 1 is of course going to become 3. Now the 2 and the 2 square, if we cancel, it's going to become a half, and similarly we could cancel the 2 and the 2 square here. So you're going to have a dy dx over 2, or you can write it as half of dy dx. Here you've got a 5 dy dx, and the plus 3 is just copied down. Then we are going to bring the dy dx to the same side and all the constants to the other side. Okay, what I have done in this case is I have gotten rid of the denominator by multiplying throughout the expression by 2. So half times 2 is going to become 1, half times 2 is going to become 1 dy dx. 5 if I times by 2, it became a 10 dy dx, and 3 if I times by 2, it's going to become 6. So now we don't have fractions, or we don't have to deal with fractions anymore. So let's now bring all the dy dx to one side. Okay, 10 dy dx minus 1 dy dx is going to give you 9 dy dx, and then of course I brought the dy dx to this side. I'm going to throw the 6 over to the other side, so it's going to become 1 minus 6. Okay, 1 minus 6 is of course going to become minus 5, and therefore the gradient of the tangent will be, okay, dy dx is minus 5 over 9. So there we have the gradient of the tangent. Now we need to find the equation of the tangent. So in order to determine the equation of the tangent is supposed to be a straight line, so it would be y equal to mx plus c. But of course we know the gradient, which is minus 5 9, so the m I can replace it with minus 5 9 x plus c. In order to determine the value of c, we need to know one set of the coordinate that the line passes through. Of course if it is a tangent to the curve at this point, of course this point would also, okay, be passing through the tangent line. So I'm going to take the 1 1 again and substitute this time into the equation of the tangent. Okay, so I'm going to replace the y with the 1 and x with a 1. So 1 is equals to minus 5/9 of 1 plus the constant c. So c is therefore would be 1 times minus 5/9 is minus 5/9, which when I throw the other side is going to become plus 5/9. So that would be 1 plus a 5/9, and that should reduce to 14/9. So we have the constant of constant here, which is the y-intercept. So now let's take this constant c and replace it into the equation of the tangent. So y is therefore equals to minus 5/9x plus 14/9. And in order to write it this way, they don't want to see any fraction. So let's multiply throughout the expression by 9. So that should give us 9y, right? Okay, is equals to minus 5x plus 14. And thereafter we can take the minus 5x and we can throw over to the left hand side, so as to write it as 9y plus 5x equals to 14, and which is of course the answer of the equation of the tangent to the curve at 1, 1 in the form that is required. So the value of a, as we can compare and see, okay, a is the coefficient of x, in this case is a 5. Okay, b is the coefficient of y, which in this case is 9, and the constant c is 14.